Logic. Logic is the art of names. Names, however, in of themselves, have no meaning. Thus, where is the art? The answer to the riddle is simple: relation to self is inadmissible, or again, the law of identity. Art is how we do our own work. So, logic is art with names. Name usage is divided between the particular and the universal. Descriptions are in the class of particulars, while definitions reside in the class of universals. As art with names is aimed at predicative behavior, this means that we like to denote the word logic as meaning the use of words for definitions, as Plato did. Logic is then the art of learning how to take particular statements in order to construct a universal definition, or as Plato described it, the ability to see the one in the many and the many in the one. This is how it is done, as Plato described. We first write up our particular example, step by step, until we reach the conclusion. This gives us an answer to that particular, which also transcribes into a quite workable universal definition. However, if one studies the chain of reasoning, one will find that many of the equations fail to work even though the final equation works perfectly. This fact has created a lot of mysticism in mathematics, such as imaginary numbers, or claims that certain figures have various cases which require each of them some new proof. Decision-making starts off, as Plato noted, with the ability to compare two things for equality. If these things are not equal, then one is less than or greater than the other. This is where logical operators come in. The logical operator is very simple. It is expressed mathematically as equals 1 or minus 1 or minus 1, that is, greater than or less than 0, or equal. A can be, however, any equation, such that every equation can become a logical operator. This means that where, on a so-called number line, they switch from 1 to minus 1, is determined by the operator itself. We learn to build these logical operators by using the geometric figure to show us where they are needed, and the figure shows us how to write them. In the basic analog mathematics sample dictionary, I show how to make logical operators from any equation. However, I did not teach much, if anything, on how to use them. Logical operators, then, teach us how to take in the moment descriptions, and turn them into functional predictive and definitive equations. I will start off with a figure which resembles the Fibonacci sequence. Here we have the mathcad write-up. We define our unit and then our other given, our input. From this we write our descriptions, which we then do, as Plato recommended, reduce each of them to the first principal parts, the unit and the verb. In this case, AE. We will find that the particulars, as written, are not always universal, and thus we have to learn how to add our if, then, else, logical operators to the equations. We now move from MathCAD to Sketchpad, turning all of our MathCAD written forms into acceptable Sketchpad forms. One will notice that all of the equations work well when E is between D and F. However, some equations are going to need a logical operator for when E goes beyond this. First we will apply a logical operator to D. Notice that it can look quite complicated, however it reduces to a simpler form, which we use MathCAD to reduce for us. Next we apply the logical operator to DH, which is quite simple. The next one is BD. And it also is quite simple to do. But notice BH's problems disappeared upon reducing it to the givens. This actually happens quite a lot. It was never wrong, but one form of it refers not to the givens directly, but includes operations which will actually work themselves out of the final product. There is no real need, or requirement to formulate myths about imaginary numbers or special cases.
False words are not only evil in themselves, but they infect the mind with evil. Phaedo by Plato,